Alright, well, I guess I didn't end this series. Did a little more testing, found a bug or two, and added some features. I think I'll just keep going on. This is kind of fun. This video will cover the bug fixes in what I have so far and take a look at new opcodes, plus expanding the register file. Do a quick refresher for parts 1 through 8. We designed a CPU and an FPGA. That CPU has 16-bit instructions. First 4 bits are opcodes, and we use 7 out of the 16 possible opcodes. There's the next 4 bits down is the register select. We coded 7 of the 16 registers. 4 of them were read-write registers and 3 were constants. We created an 8-bit address data bus peripheral interface designed specifically for the group of multi-comp peripherals that exist, but it should work with pretty much any 8-bit peripheral out there, which is pretty much everything out there. We have found that its performance that we can achieve is 12.5 MIPS, 4 clocks of a 50 megahertz clock per instruction performance, which is a pretty good performance. Definitely places it in a class above 6502 back in the day. We have a 12-bit address space for the code, which says we can have up to 4K of instructions, limited by those 12 bits. And that peripheral support, as I mentioned, has 8 bits of address and 8 bits of data in and out. The objective of this video is to add the OR with immediate value instruction. Yeah, there's a backwards parentheses there. Further test the CPU and fix any bugs we find that were in the original design. While we were doing this, notice that the AND register immediate instruction was not writing back after the AND. It was working in our test cases so far because all we did was do ANDs and then branches, so that worked, but it wasn't writing back to the register. We noticed that when we added in the OR because it wasn't writing back either, and we added 4 more registers to the register file, giving us 8 read-write registers plus the 3 constants that we already had. The OR immediate opcode or instruction was added immediately after the AND register immediate instruction. It has an opcode bit field of 9 in hex, and the next bits just like the AND register immediate, the 4-bit register number followed by an 8-bit immediate value. We have to add into the ALU that particular function. It's really pretty simple to add it. We added into the entity itself a control line that indicates that the OR immediate instruction is being, or the register immediate instruction is being executed currently, and added a second line here into the ALU output that is the bitwise AND of ALU A in and ALU B in, and operates when that OR instruction happens. That's why when we built the ALU originally, we put in the ARI test there, knowing that we would expand it out here for other arithmetic operations. We could have easily added an XOR while we were there. Might have been worth doing. There's quite a few changes in the CPU itself. To the signal list, we added that opcode to create a wire for that signal. Probably should have named all these W underscore something. That would have been the right thing to do, but we didn't. And maybe I'll fix that when I go back in here. Into the list of opcodes that are created, we added the ORI that's true when that 9 is set up in those 4 bits of the opcode. The register file in, we added in the 2 lines here for the ARI and the ORI. That was missing in the previous code, but we added it in. We'll see that show up here. And for the ALU unit itself, we added to the entity instance in CPU 001, added the OR and then said latch that Z bit for either the OR or the AND instructions, either one, still at the same gray code value of 2. So that was really all we had to do for the code to get it basically in there. Went to test it and wrote a little piece of code that cleared register 0 and then set register 0 to, or ORed it with 55. The result should have been 55, and then ORed that with AA, and the result of that should be FF. In a listing file from the assembler is exactly what we would expect, with the new opcode 9 being generated. When we went to do it, we found out that the write back to the register after the ARI and the new ORI instruction wasn't happening. We fixed and it's now working. You can see the FF out here. So you can see that it took the 55 through, ORed it with the AA, and produced an FF, just like it should. The two lines that were changed to do that were the wload register file, so that gets loaded when the ARI and the ORI are set, same gray code. And what we really are seeing is that we need a good instruction test program. The ARI was really operating more like a bit test. It was not destructive back to the register if you did the AND, which meant it worked fine for the branches. The branches just look at the Z bit after the AND, and it worked fine with things like status registers where you read it and want to just test the bit. So essentially a bit test instruction where it doesn't change the original register. And maybe that's a better thing to code, maybe it isn't, but it's something we're going to do is to make it destructive. We want to be able to mask off bits in a register, and this is really the only way we're going to get there. Next thing we want to do is expand the register file, and that is not very difficult at all. It was designed to be expanded. Inside of the register file, VHD file, we add the 4 registers, and they're all standard logic vectors just like the original 4 were. In the part of the code, which is the register file process, we add those 4. Something we also did was recode to hex values. Instead of being double quote 0, 0, 0, 0, double quote, we changed it to X, double quote 0, X. That says it's a hexadecimal value, 0 through F if it's a single digit like this. Has to be in double quotes because it's not like a 1 or a 0. And added 4, 5, 6, 7 down here, and the registers are 4, 5, 6, and 7. If you double click in the signals list, you can see one of these light up at a time. Inside Quartus, there's an exception to that. If you double click and you have the replace, search and replace open, it won't show the other places where that particular thing that you double clicked is. But if you shut off those searches by closing the boxes for them, it will show up in all the places. So if you double click through the signals list one at a time, double click on reg 0 and then look down here, you see it just lights up that one spot. Do all the way through for 7. I found the typo on one of them that way. It's saves you the time of compiling and having it not work. In the output multiplexer, which is the register output multiplexer back, we added 4, 5, 6, 7, did the same thing with recoding the hex values here. We still have those 3 constants in any unused registers, which is getting smaller now. It would be A, B, C, D, E, so 5 uncoded registers would all be set to 0. Well, we've already got a 0 if you do 8, so we could put those in if we want. We could leave them out if we want, but for now we'll just leave them out. I think 8 registers is more than anything I've used in any of the applications I've done so far. It's a pretty good size. Okay, let's test that register file, the larger register file we created, by filling up each of the registers 1 through 8 with bouncing bits, or bit that bounces 1, 2, 4, 8, 10, 20, 40, 80, and hex values, and just go through and do an IO write of each of those out to address 0, and then look in signal tap and see what it did. We don't really care whether it actually did an IO write, but we just want to look and see data going out. So when we do that, we see that does all the loads here, 1, 2, 4, 8 through 80, and we can see the writes out here as well, the IO writes. 1, 2, 4, 8, 10, 20, 40, 80. So it worked. The register file now has 8 registers, and they're all 8 bits. Not bad. Added this branch in, created a branch for this appendix. We're going to call it Appendix 1. Keep away from the numbers that already got messed up. So Appendix 1 or A1. And as usual, the GitHub repository for the CPU itself is back here. You can trim back the same path here if you wanted to. But that branch does have this ARI fix. It does have the extra registers. And it adds the ORI. So nice little baby step, but thought we'd put it out there.
If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well.
We have a store in Tindy where we sell all of our cards.
Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.